The Routing Information Protocol is one of the oldest distance vector routing protocols, which employs the hop count as a routing metric. RIP prevents routing loops by implementing a limit on the number of hops allowed in a path from the source to a destination. The maximum number of hops allowed for RIP is 15. This hop limit, however, also limits the size of networks that RIP can support. A hop count of 16 is considered an infinite distance, in other words the route is considered unreachable. RIP implements the split horizon, route poisoning and hold-down mechanisms to prevent incorrect routing information from being propagated. Originally, each RIP router transmitted full updates every 30 seconds. In the early deployments, routing tables were small enough that the traffic was not significant. As networks grew in size, however, it became evident there could be a massive traffic burst every 30 seconds, even if the routers had been initialized at random times. It was thought, as a result of random initialization, the routing updates would spread out in time, but this was not true in practice. Floyd and Van Jacobson showed in 1994 that, without slight randomization of the update timer, the timers synchronized over time. In most current networking environments, RIP is not the preferred choice for routing as its time to converge and scalability are poor compared to EIGRP, OSPF, or is, and a hop limit severely limits the size of network it can be used in. However, it is easy to configure, because RIP does not require any parameters on a router unlike other protocols. RIP uses the user datagram protocol as its transport protocol, and is assigned the reserved port number 520. Versions: there are 3 versions of the Routing Information Protocol, RIPv1, RIPv2, and RIPNG. RIP version 1, the original specification of RIP, defined in RFC 1058, was published in 1988 and uses class file routing. The periodic routing updates do not carry subnet information, lacking support for variable-length subnet masks. This limitation makes it impossible to have different-sized subnets inside of the same network class. In other words, all subnets in a network class must have the same size. There is also no support for router authentication, making RIP vulnerable to various attacks. RIP version 2, due to the deficiencies of the original RIP specification, RIP version 2 was developed in 1993 and last standardized in 1998. It included the ability to carry subnet information, thus supporting classless inter-domain routing. To maintain backward compatibility, the hop count limit of 15 remained. RIPv2 has facilities to fully interoperate with the earlier specification if all must be 0 protocol fields in the RIPv1 messages are properly specified. In addition, a compatibility switch feature allows fine-grained interoperability adjustments. In an effort to avoid unnecessary load on hosts that do not participate in routing, RIPv2 multicasts the entire routing table to all adjacent routers at the address 224.0.0.9, as opposed to RIPv1 which uses broadcast. Unicast addressing is still allowed for special applications. MD5 authentication for RIP was introduced in 1997. RIPv2 is Internet Standard 56 Sautom and Principe DOBAS. Route tags were also added in RIP version 2. This functionality allows for routes to be distinguished from internal routes to external redistributed routes from EIGRP protocols. RIPNG, defined in RFC 2080, is an extension of RIPv2 for support of IPv6, the next-generation Internet Protocol. The main differences between RIPv2 and RIPNG are, support of IPv6 networking. While RIPv2 supports RIPv1 updates authentication, RIPNG does not. IPv6 routers were, at the time, supposed to use IPsec for authentication. RIPv2 allows attaching arbitrary tags to routes, RIPNG does not. RIPv2 encodes the next hop into each route entries, RIPNG requires specific encoding of the next hop for a set of route entries. RIPNG sends updates on UDP port 521 using the multicast group FF029. RIPv1 operation. RIP defines two types of messages. Request message, response message. When a RIP router comes online, it sends a broadcast request message on all of its RIP-enabled interfaces. All the neighboring routers which receive the request message respond back with a response message containing their routing table. The response message is also gratuitously sent when the update timer expires. On receiving the routing table, the router processes each entry of the routing table as per the following rules. If there are no route entry matching the one received, then the route entry is added to the routing table automatically, along with the information about the router from which it received the routing table. If there are matching entry but the hop count metric is lower than the one already in its routing table, then the routing table is updated with a new route. If there are matching entry but the hop count metric is higher than the one already in its routing table, then the routing entry is updated with hop count of 16. The packets are still forwarded to the old route. A hold-down timer is started and all the updates for that from other routers are ignored. If after the hold-down timer expires and still the router is advertising with the same higher hop count, then the value is updated into its routing table. Only after the timer expires, the updates from other routers are accepted for that route. Timers. The Routing Information Protocol uses the following timers as part of its operation: 1 update timer, 2 invalid timer, 3 flush timer, 4 hold-down timer. Update timer. The update timer controls the interval between two gratuitous response message. By default the value is 30 seconds. The response message is broadcast to all its RIP-enabled interface. Invalid timer. The invalid timer specifies how long a routing entry can be in the routing table without being updated. This is also called as expiration timer. By default, the value is 180 seconds. After the timer expires, the hop count of the routing entry will be set to 16, marking the destination as unreachable. Flush timer. The flush timer controls the time between the route is invalidated or marked as unreachable and removal of entry from the routing table. By default the value is 240 seconds. This is 60 seconds longer than invalid timer. So for 60 seconds the router will be advertising about this unreachable route to all its neighbors. This timer must be set to a higher value than the invalid timer. Hold-down timer. The hold-down timer is started per route entry, when the hop count is changing from lower value to higher value. This allows the route to get stabilized. During this time no update can be done to that routing entry. This is not part of the RFC 1058. This is Cisco's implementation. The default value of this timer is 180 seconds. Limitations. The hop count cannot exceed 15, otherwise it will be considered invalid. Most RIP networks are flat. There is no concept of areas or boundaries in RIP networks. Variable length subnet masks are not supported by RIP version 1. RIP has slow convergence and count to infinity problems. Implementations. Cisco iOS, software used in Cisco routers. Cisco NXOS, software used in Cisco Nexus data center switches. Junos, software used in Juniper routers, switches, and firewalls. Rooted and Route 6D, included in most BSD Unix systems. Routing and remote access, a Windows Server feature, contains RIP support. Quagga, a free open-source routing software suite based on GNU Zebra. Bird, a free open-source routing software suite. OpenBSD, includes a RIP implementation. Similar protocols. Cisco's proprietary interior gateway routing protocol was a somewhat more capable protocol than RIP. It belongs to the same basic family of distance vector routing protocols. Cisco has ceased support and distribution of EIGRP in their router software. It was replaced by the Enhanced Interior Gateway Routing Protocol, which is a completely new design. While EIGRP still uses a distance vector model, it relates to EIGRP only in using the same routing metrics. EIGRP supports multiple metrics for each route, including bandwidth, delay, load, MTU, and reliability. See also, OSPF, BGP, route poisoning, split horizon, convergence. References. Further reading, Malkin, Gary Scott. RIP, an intra-domain routing protocol. Addison Wesley Longman. ISBN 0-201-43320-6. Edward A. Taft, Gateway Information Protocol, Xerox System Integration Standard, Internet Transport Protocols, External Links.